In this lesson, we will discuss the process of electrolysis. Electrolysis is the decomposition of a compound in molten or aqueous state by passing an electric current through it. Electrolysis in molten state involves binary electrolyte in which only two ions from molten compound are separated by passing electric current in them. The animation below shows electrolysis of molten lead-2 bromide solution.
The Earth's crust contains many compounds. But the compounds themselves aren't as useful to us as the elements they're made up of. This rock contains aluminium oxide. Split the aluminium from the oxygen and you have one of the world's most useful metals. You can split a compound using electricity. The idea is to pass an electric current through it, a process known as electrolysis. A circuit is set up using two carbon electrodes, an ammeter and a power supply. The white powder is lead bromide. Switch on the power supply and nothing happens. The ammeter reads 0. Solid lead bromide doesn't conduct electricity. It needs to be molten. Lead bromide melts at 370 degrees Celsius. Switch on now and a current flows. In this circuit, the electrode on the right is positive. The one on the left is negative. As electricity passes through the molten lead bromide, chemical reactions start. On the left, at the negative electrode, nothing appears to be happening. But at the positive, bubbles mean a gas is being produced. Placing small tubes around the electrodes traps any gas, making it easier to see their colour. What could the brown gas be? The gas is bromine.
Molten lead-2 bromide solution contains two ions, lead ions and bromide ions. During electrolysis, the molten compound is decomposed such that lead-2 ions migrates towards the negatively charged electrode or cathode, where it is deposited as grey solid. The equation at the cathode is bromide ions, on the other hand, will migrate towards the positively charged electrode or anode, where it is evolved or released as red-brown fumes of bromine gas. The equation at the anode is as follows. Note that the reaction is an oxidation reaction. Electrolysis of aqueous solution is different from that of molten solution because water as a solvent dissolves ionic compounds, making the ions free to move in the solution as ions. In the process, water dissociates into hydrogen ions and hydroxide ions. Together with ions of the compounds dissolved, the cations from the compound and hydrogen ions from water migrate to the cathode, while anions from the compounds and hydroxide ions from water migrate to the anode. The ions from dissolved salt and those from dissociated water compete for discharge at the respective electrode, but at each electrode, only one type of ions get discharged. This is called preferential discharge. Position of the metal in the electrochemical series. The case of discharge of ions during electrolysis depends on their position in the electrochemical series. Metals in this series are placed in an increasing order of their ability to lose electrons. Non-metals are placed in an increasing order of their ability to gain electrons. The video clip below shows the electrolysis of dilute sodium chloride. Click to play the video and observe what happens carefully. The electrolysis of dilute sodium chloride. Procedure. Have filled the beaker with dilute sodium chloride solution. Switch on current. Observe what happens on the electrode. Test the gases collected with a glowing and burning spirit. Sodium and hydrogen ions in aqueous migrate to the cathode. Hydrogen ions are preferentially discharged to sodium ions because it is lower in the electrochemical series. It gains an electron to form hydrogen atom. The hydrogen atoms combine to form hydrogen molecules. Chlorine ion and hydrogen ions migrate to the anode. Hydrogen ions are preferentially discharged because it is lower in electrochemical series. The overall equation is: note that the volume of hydrogen gas produced is twice that of oxygen gas produced. This is shown in the mole ratio in the equations at the anode and cathode. Hydrogen ion is easily discharged at the cathode compared to sodium ions, while hydroxide ions are preferentially discharged at the anode compared to the chloride ion. The ease of discharge of ions during electrolysis of various solutions are summarized in the table below. We have observed that ions lower in the electrochemical series will be preferentially discharged under normal conditions. However, if the ion that requires more energy to discharge is present in greater concentration than the other one lower in the electrochemical series, it will be discharged preferentially. Click to play the video clip to observe electrolysis of concentrated sodium chloride or brine solution.
Sodium chloride is one of the world's cheapest and most widely available raw materials. It's found as rock salt in vast deposits underground, and it's dissolved in all the oceans of the world. The electrolysis of sodium chloride solution is an important industrial process. Mix the salt with water, pass an electric current through it, and a variety of useful substances are produced. To work out what's going on, here's a much simpler setup in the lab. Two electrodes immersed in sodium chloride solution are connected to a power supply. The electrodes are made of carbon. They're supported by an insulated hook. See what happens when an electric current is passed through the solution. What evidence is there that chemical reactions are taking place? Bubbles appear around both electrodes, a sign that gases are being produced. To collect the gases, a test tube full of sodium chloride solution is placed over each electrode. Gas displaces the solution and collects in the top of the tube. So, what are the gases? Both are either very pale or colourless, but they can be identified by simple tests. The gas collecting at the positive electrode is tested with damp blue litmus paper. It goes red and quickly bleaches white. The gas is chlorine. The gas collecting at the negative is tested with a lit splint. It pops, a sure sign that this gas is hydrogen. So, why does the electrolysis of sodium chloride solution produce hydrogen and chlorine? Imagine you can see the charged particles in solution. There are sodium ions, which are positive, and chloride ions, which are negative. The others are present in water, positive hydrogen ions and negative hydroxide ions. These different charged particles are all free to move. Once the power supply is switched on, the positive ions are attracted to the negative electrode. The negative ions move towards the positive. Sodium and hydrogen compete to gain electrons. The hydrogen ions win out. They lose their positive charge and form bubbles of hydrogen gas. Competition also happens at the positive electrode. This time, chloride ions win out, losing their negative charge and forming bubbles of chlorine gas. Industrially, the electrolysis of sodium chloride solution can provide us with many useful materials.
At the cathode, sodium ion and hydrogen ions migrate. Their hydrogen ions are discharged in presence to sodium ions because hydrogen ions are lower in electrochemical series than sodium ions. The equation at the cathode is as follows. A colorless gas is produced which extinguishes a burning splint with a pop sound. At the anode, chlorine and hydroxide ions migrate towards there. Although hydroxide ion is lower in the electrochemical series than chlorine, the concentration of chlorine ions at the cathode is greater than the hydroxide ions. Therefore, chlorine ions are discharged in preference to hydroxide ions. The gas produced bleaches moist litmus paper and is green-yellow in color and is therefore chlorine. The concentration of ions in solution determines the products at the respective electrodes. A cation or an ion whose concentration is high is preferentially discharged if the ions are close in the electrochemical series. During electrolysis of concentrated sodium chloride, hydrogen ions and chlorine ions are discharged while sodium ions and hydroxide ions are left in solution. This makes the resulting solution alkaline. The choice of electrodes during electrolysis can alter the order of discharge of the ions. To discuss this, consider electrolysis of copper 2 sulfate solution using graphite electrodes and copper electrodes. Electrolysis of copper 2 sulfate solution using inert electrodes. Click to play the video to observe what happens. The choice of electrodes during electrolysis can alter the order of discharge of the ions. To discuss this, consider electrolysis of copper 2 sulfate solution using graphite electrodes and copper electrodes. Electrolysis of copper 2 sulfate solution using inert electrodes. Click to play the video to observe what happens. At the cathode, both copper ions and hydrogen ions migrate towards it. Copper ions gain electrodes to form copper metal, which appears as brown deposits. Copper ions are therefore preferentially discharged. The equation for the reaction is, at the cathode, sulfate ions and hydroxide ions migrate. However, hydroxide ions preferentially lose electrons, being lower in the electrochemical series. They combine to form water and oxygen gas as shown in the following equation. Copper ions give copper 2 sulfate solution the blue color. As these ions are discharged and deposited at the cathode as copper solid, the color of the solution fades and will eventually become colorless. Having removed the copper and hydroxide ions from solution, hydrogen ions and sulfate ions remain, forming sulfuric acid.
Electrolytic refining of copper. Electrolytic refining is a process of obtaining
Copper 2 ions make copper 2 sulfate solution blue. Copper 2 ions make copper 2 sulfate solution blue. For each ion removed at the cathode, it is replaced when copper dissolves at the anode. Therefore, the solution remains blue and the concentration of the solution remains constant. Note that the mass lost at the anode is equal to the mass gained at the cathode. In this lesson, we will discuss quantity of electricity.